Okay, so now we're going to talk about graph coloring. So basically for graph coloring, um, if I want to assign each of these vertices a color such that it is not adjacent to the same color. So if I have, say I go this guy, I can assign this guy red, I can assign this guy black, and I can assign this guy, sorry, and I can assign this guy blue. Okay. Technical difficulties there. Let's call this guy gray. Cool. So this graph is 3 colorable. And if I have a tree, any tree, then it's definitely 2 colorable. I can assign these guys colors such that it doesn't share the same color with an adjacent vertex, and such that each color is unique. Oh, sorry, not that each color is such that it's not touching the same color, so it's not adjacent to the same color. I can do that with 2 colors for any tree because I just take one of my starting points, and then as I construct, I introduce a new node, and let's say I color the first guy red, and I color the next guy blue, and then my next node is going to attach to either one of these guys, say it attaches to blue, then I color it red, and I can keep going with that. It turns out that I can do something similar with even cycles. So I can do red, blue, red, blue. But I can't quite get away with 2 for odd cycles. So, and I can do the same thing of if I have an even cycle and then I have kind of a tree attached to it, then I can keep on going. Red, blue, blue, red, red. I can grow it out like this. So we have a theorem that says a graph is 2 colorable if and only if it does not contain any odd cycles. Any odd cycle, is 3 colorable, but not 2 colorable. And you can run through that and see, give yourselves either straight up prove it to yourself or just kind of demonstrate it for yourself on enough low cases. Once you see it for a few low cases, you should be able to extrapolate the proof out from there. We also have a few other theorems. If a graph is of constant degree d, then it is d plus 1 colorable. That tells us that we can color it in at least d plus 1, not necessarily that it must be d plus 1. We could, in theory, cover it with less. And an example where we cover it with less is an even cycle. So even cycles are decolorable. Another interesting, important guy to keep track of is any graph that represents the adjacency of regions of a map is four-colorable. This was kind of the first high-profile computer proof. They had to run through thousands and thousands of different cases to show that this works. And in all of them, and that was the first major computer-assisted proof, and it was pretty controversial for a while. It's actually very easy to show that this is true for 5 or 6. So if you guys want to try to prove that for yourselves, but don't bother trying to prove the 4-color yourself. So that's basically what I mean by adjacency is if I have a map that looks like, say this is my map and then blah, 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 blah. Then I would turn this into one vertex, I would turn this into another vertex, blah, blah. And then I would connect it to each of the ones that it's adjacent to. And if I can do this, then I can guarantee that it is 4-colorable. I think that's everything that I need to show for this section.